Welcome to The Explainer. Today, we're basically becoming chemical detectives. We're going to tackle a case that's at the very heart of all modern chemistry. How in the world do you figure out what things are actually made of? So let's just jump right in. Imagine you have to write a recipe for a molecule. The catch? You can't see a single one of the ingredients, the atoms themselves. I mean, where would you even begin? This isn't just a brain teaser. This was the exact frustrating puzzle that stumped chemists for years. So, what's the short answer? Well, they really didn't know. Somebody on Reddit put it perfectly. It was a long, hard slog. Scientists could tell that elements combined in specific ways, but actually figuring out the exact recipe for something simple like water, let alone a complex sugar molecule, well, that was a huge, huge challenge. Okay, so let's follow the breadcrumbs. We're going to retrace the steps of these early scientific detectives as they pieced together this giant puzzle, and in doing so, discovered the very building blocks of our world. Our investigation kicks off with the very first solid clue that chemists could actually get their hands on, and that was finding the simplest possible ratio of atoms in a compound. This right here was the first real break in the case. And this brings us to two really important terms. Our first clue, that simplest ratio, is called the empirical formula. Then there's the final answer, the thing we're really after, which is the molecular formula. That's the true recipe with the exact count of every single atom. The key thing to remember, they're not always the same thing. Just look at these examples. They make it super clear. For hydrogen peroxide, the simplest ratio you can have is just one hydrogen to one oxygen, HO. But the actual molecule is H2O2. Same thing for glucose. The simplest ratio is CH2O, but the real sugar molecule is way bigger, C6H12O6. So you can see the empirical formula is a fantastic clue, but it is not the whole story. So, just to lock this in, the empirical formula is our starting point. It's the simplest whole number ratio of atoms you can have in a compound. For our early chemical detectives, this was the first piece of hard evidence they could get time and time again. So how did they find this ratio? It definitely wasn't just guesswork. Nope. It was a reliable 5-step investigation, a standard procedure that chemists perfected over time. So let's walk through that process. Here it is, the 5-step playbook. First, you figure out the mass of each element in your sample. Second, you convert that mass into a universal unit called a mole. You can think of it like a chemist's version of a dozen, just for a massive number of atoms. Third, you divide to find the simplest ratio. Fourth, you do a quick multiplication to get rid of any pesky fractions. And boom, fifth, you write down the formula. This flow chart here shows the roadmap perfectly. See how we start at the top with either percentages or mass? Then we just follow the arrows down, convert to grams, then to moles, and then we run our division and multiplication steps, and it leads us right to our first big clue, the empirical formula. Okay, enough theory. Let's see this thing in action. We are going to solve a real case here. It involves a compound that's used in the brewing industry to keep all the casks and vats clean. Now, lab analysis tells us it's made of about 35% potassium, 29% sulfur, and 36% oxygen. All right, let's run the numbers. Step 1 is super easy. We just assume we have 100-gram samples, so the percentages just turn into grams. Easy. For step 2, we've got to convert those grams into moles. We do that by dividing by each element's atomic mass. You can just look that up on a periodic table. And as you can see, that gives us the relative number of moles for each element. But the numbers are still kind of messy. And now for the really clever step, the one that simplifies everything. We take our 3 mole values and we divide each one by whichever of the 3 is the smallest. And just like that, it cleans up the ratio. We get 1 potassium for every 1 sulfur for every 2.5 oxygen. Okay, we are getting really close. But wait, you can't have half an atom in a formula. So for step 4, we just multiply that whole ratio by 2 to get rid of the fraction. And that leaves us with the beautiful, clean, whole number ratio. 2 potassiums, 2 sulfurs, and 5 oxygens. And there you have it. Our first clue is officially in the evidence bag. The empirical formula is K2S2O5. But hold on, our investigation is not over yet. We've got the simplest ratio, sure, but is it the true formula? Or could the real molecule be some multiple of this, just like we saw with glucose earlier? To crack this case wide open, we need one last piece of evidence. And that final clue is the total weight of the entire molecule, what we call its molecular mass. Think of it like this. If we know the weight of our simplest little building block, and we can also measure the weight of the whole building, it's pretty easy to figure out how many blocks make up the real thing. And this simple little formula is the key that unlocks the whole mystery. You just take the true molecular mass and divide it by the mass of your empirical formula. The answer you get, we just call it N, tells you the exact whole number you need to multiply your simple ratio by. So this roadmap shows exactly how it all comes together. We take our two big clues, the empirical formula and the molecular mass, we combine them with that one simple division step, and it points us straight to the final answer, the true molecular formula. Okay, let's solve one last case. This one involves a pretty serious environmental pollutant, polychlorinated biphenyls, better known as PCBs. So we've got the percentages for carbon, hydrogen, and chlorine. And this time, we also have that final critical clue. The total molecular mass is 360.88. All right, first up, our detectives get to work finding that empirical formula. They followed the exact same 5-step playbook we just went through. Convert the percentages to moles, find the simplest whole number ratio, and the result they get for this PCB is C6H2Cl3. And now for the final reveal. We take the molecular mass we were given and divide it by the mass of our C6H2Cl3 unit. The answer comes out to almost exactly 2. That tells us the real molecule is twice as big. We multiply everything by 2 and we get the final, true molecular formula, C12H4Cl6. Case closed. So, why does all this careful, step-by-step detective work matter so much? Well, it's because this process, this ability to reliably figure out a compound's formula, is what transformed the ancient guesswork of alchemy into the precise science of modern chemistry. It gave us the key to crack the entire chemical code. So what's the big takeaway here? It's this. The empirical formula is your first clue, the simplest ratio. The molecular formula is the real prize, the actual count of atoms. And that molecular mass, that's the key that connects the two. This whole process is the absolute bedrock of how we understand, identify, and create pretty much every material that shapes our lives. You know, this method for cracking the chemical code is more than 150 years old, but it is still used every single day in labs all over the world. It really makes you wonder, doesn't it? From designing new medicines that save lives to discovering materials for a more sustainable future, what modern puzzles are we solving with this classic technique right now?